Designing any physical or digital system requires extracting absolute maximum performance from a strict set of unyielding boundaries. You never have infinite resources. You have exact physical limits. Translating those physical limits into calculable numbers requires a mathematical discipline known as linear programming. Linear programming is the structural art of formulating a problem space. You define the exact goal you want to achieve, and you set the strict limitations holding you back. We do this because we are not looking for a generally favorable outcome. We construct this formula to mathematically guarantee the single optimal outcome. We are going to build this geometric model from the ground up, map its logic across aerospace, apply it to electronics and cloud computing, and finally execute it in Python. Without this structural logic, engineers are simply guessing at efficiency. With it, they can prove absolute maximum performance. This blank Cartesian coordinate plane represents pure mathematical space. We start with pure algebra. The first component placed on this plane is the objective function. Represented by the variable z, this linear equation targets a strict direction. You either want to maximize this function, pushing for the highest possible profit, yield, or thrust, or minimize it, driving down latency, weight, or cost. The second component is the constraints. These are the strict limitations imposed by the physical world, like the maximum heat a material can withstand, or the exact budget you have available. Mathematically, we model these limitations as linear inequalities. These linear boundaries snap onto the plane, intersecting and cutting off sections of the grid. The overlapping shaded polygon is the feasible region, the only area where all constraints are simultaneously true. This brings us to the fundamental theorem of linear programming. Watch the corner points of this polygon pulse. The theorem dictates that the mathematically optimal solution will always exist exactly at one of these vertices. Optimization is a geometric reality. The absolute best answer is always trapped in a corner. Watch the axes update as we map this geometry to an aerospace problem. We are optimizing a satellite launch profile. The x-axis becomes payload mass, and the y-axis becomes propellant volume. The objective vector is now explicitly labeled max delta v, maximizing velocity change. A rigid cubic volume limit inside the fairing dictates our first constraint line. You cannot pack more mass than it holds. The booster's maximum thrust-to-weight lifting capacity drops in as a second limit, completely closing off our feasible region. By identifying the optimal vertex on this polygon, we find the exact ratio of payload to fuel. This mathematically perfect balance prevents us from physically snapping a fairing under pressure or becoming entirely too heavy to achieve orbit. Let's reset the axes and switch to electronics. We are now designing power logic for a system on a chip. The x-axis tracks CPU power, and the y-axis tracks neural processing unit power. Our new objective function is to maximize total computational throughput, measured in teraflops. The battery imposes a strict cap. A horizontal limit line locks the total power draw at exactly 15 watts. To prevent the silicon from melting, an intersecting angle line establishes the cooling capacity, known as the thermal dissipation limit. The optimal vertex of this new polygon dictates the precise wattage split, say 9 watts to the CPU and 6 to the NPU, that yields the highest calculation speed right on the edge of thermal failure. The scale of a rocket booster and a microchip could not be more different, yet the underlying geometric constraints are identical. The diagram updates a third time for software architecture. We are running a Kubernetes cluster, mapping database pods against web server pods. Our software objective function is to maximize the number of concurrent user requests the web application can handle. Physical hardware forces our constraints. These two overlapping lines represent the total physical RAM of the server rack and the available virtual CPU cores. Exceeding these precise lines in a cloud environment triggers critical out-of-memory crashes, forcefully taking the entire system offline immediately. The optimal vertex determines the exact ratio of database to web pods needed to hit 100% hardware utilization without crashing. We can line these three scenarios up side by side. The labels change, but the algebraic structure remains constant. Whether an engineer is balancing physical mass, thermal heat, or virtual memory, the mathematical framework is universal. To put this universal geometry to work, we have to translate these enclosed polygons into algorithmic solvers. In this split screen, the electronics feasible region sits on the left, and the Python library SciPy Optimize linprog sits on the right. Watch vectors draw dynamically from the graph's limits directly into the inequality matrix arrays within the code. There is a specific engineering trap hidden in this library's default behavior. The linprog algorithm is strictly biased toward minimization problems. This creates a direct conflict when your objective is to maximize something like teraflops or orbital delta V. Notice how the objective function values in the script flash as a negative sign is forcefully inserted. Engineers must mathematically invert the signs of their objective function coefficients before running the script. Code is the execution layer. The actual engineering happens in the geometric reasoning. Look back at this full-screen complex feasible region. That pulsing highest vertex is our current maximum limit. But physical constraints are rarely static. Engineers actively alter physical reality. They install a copper heatsink on a chip or upgrade RAM capacity. Adjusting a physical limit pulls the constraint line outward on the graph. This expands the polygon and unlocks a new, higher optimal vertex. Optimization is a rigid geometric reality. By mastering the precise formulation of objective functions and constraints, you remove all guesswork from systems architecture. Discovering this optimal vertex mathematically proves that a physical system is operating exactly at the absolute limit of physics. Linear programming is the definitive language for maximizing engineered systems.